Welcome to today's lesson. Today we're talking about fluid pressure, and many statics books put fluid pressure in the centroids chapter. And people go like, why in the centroids chapter? But if you actually look at a typical fluid pressure distribution, what you have, if you have a straight dam or a straight plate or a gate of some kind, or even a curved surface, you basically have a fluid pressure distribution on that surface, and so it's a distributed load. In fact, we've done distributed loads in this class throughout the class, but we really haven't talked much about instances that produce distributed loads. But fluid pressure is a classic example of that. So it's in the centroids chapter because ultimately what we're looking for is to find the resultant force, which is basically the volume of that pressure distribution, and then we're looking for its location, and it's basically the centroid of that distribution. And so that's why it's in the centroids chapter. So some rules about fluid pressure that you need to know. Rho GH, pressure is equal to rho GH, where rho is a mass density, G is a constant of gravitation, and I like to use H as a depth from the free surface. Some books use Z, but I'll refer to it as H. So rho GH, but I prefer to use gamma. So gamma is a specific weight, and that's equal to rho times G. And so then basically, if you refer to pressure as gamma times H, then basically if you have a free surface, and you have a plate down here somewhere, and this is some H1, and this is some H2, then basically the pressure at this point is gamma H1, and the pressure here is gamma H2. And you end up with a trapezoidal shaped pressure distribution. But basically, anytime you need a pressure, it's just gamma times H. And so what's the number for gamma? So if I asked you what the mass density of water is, you'd probably say, well, 1 gram per cc. If you actually go to the second side of this sheet, and if you look at a meter by a meter by a meter, if the mass of density is 1 gram per cubic centimeter, then in a liter, you've got 10 centimeters by 10 centimeters by 10 centimeters. So a liter is 1,000 grams of fresh water. But there's 10 times 10 times 10 liters in a meter. So there's 1,000 liters, each with 1,000 grams. So in a cubic meter of fresh water, you have 1,000 kilograms of mass. And so in the SI system, mass density is 1,000 kilograms per cubic meter. But then we multiply that times 9.81. And so for fresh water, we get gamma is equal to 9810 newtons per cubic meter. And that's a specific weight. And again, so that's in the SI system for fresh water. In the US system for fresh water, gamma is basically 62.4 pounds per cubic foot for fresh water. Obviously, if the water has solids dissolved in it, my background is petroleum engineering. If you dissolve clay in it or barite or some weighting material, then the gamma will be higher than that. But this is for fresh water. And so these are the terms we most often use. Sometimes a book will give you a density of the water, and they'll say like 1, so rho is equal to 1 megagram per meter cubed. So this megagram is 10 to the 6th grams per meter cubed. But that's basically the same thing as 1,000 kilograms. So 1,000 kilograms per cubic meter. And so I much prefer this over this. But if you're given that, you have to convert to this. And then again, multiply that rho times 9.81 to get 9810. So that's rho and that's gamma. So our rules of pressure. So rule number one is pressure is a function of depth. And so at any depth, you're going to have the same pressure. Rule number two is that pressure will always act perpendicular to a surface. And so if you draw a picture of a cave or a tunnel or a channel or something like that at a given depth, so we have a cave that looks like this. At a given depth, that's some depth h or z below a free surface. The pressure at this depth is always the same, but it acts perpendicular to a surface. So it's going to act perpendicular to this guy. 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 But all of those pressures are exactly the same as one another, but they're going to act perpendicular to a surface. So whenever we draw a plate, a submerged plate, we're going to always draw the pressures perpendicular to that plate. Or if we have a curved surface, and this is where it gets challenging, the pressures act perpendicular to that curved surface. Okay, so pressures are a function of depth, gamma h, and they're perpendicular to any surface. While we're at it, I'll just mention one more thing. If you actually have a submerged object here, it actually has pressures that act all around it, just like this. And the pressures that act across the top of the sky are slightly smaller than the pressures that act below it because they're at a different depth. And so if you actually take this ball and kind of draw it larger, if you resolve all of these forces into horizontal and vertical components, you got all these verticals here, all these verticals here, and then all of these forces have horizontal components. All the horizontal components cancel one another out. And so these guys are larger than these guys, and the difference between the vertical components of these guys and the vertical components here, the difference in those two is Archimedes' principle. It's the buoyant force that basically acts upward on this guy. And so if you remember Archimedes basically says that on a submerged object, there's an upward directed force whose magnitude is equal to the weight of the fluid that is displaced. And so this is a way of kind of understanding how Archimedes works. So pressure is a function of depth. Number two, it acts perpendicular to a surface. So the problem in this particular unit, what we're trying to do is we're trying to find the resultant force. And so the most fundamental fluid pressure problem is finding the volume of the pressure distribution. And so it's basic. So whatever that pressure distribution is, whether it's a strange guy with a variable width plate, or whether it's a straight, flat, constant width plate or whatever, we get a pressure distribution. And so what we're looking for is Fr is equal to the integral over the area of the pressure times dA. And so if you have a pressure acting on a dA, pressure times dA is force. And so we're adding up all of those forces to get the resultant force. And so that's what we're doing on every problem. Now there's techniques or tricks we're going to use for different kinds of problems, but fundamentally, this is really what we're doing on every problem.